Hello and welcome to my Physics Lab 2 presentation. The goal of this lab was to observe an object's motion when dropped at rest, meaning that it had an initial velocity of 0 meters per second. My chosen object was a crumpled piece of paper. In observing the object's motion, 3 different predictions or models were created. One was the observed prediction using a recording of the falling object and tracker. The other 2 were computational models, with one only accounting for gravitational force and the other including gravitational and drag force. The results of the lab conveyed that predictions were more accurate and aligned with real-world observations as more forces were taken into consideration. For the observed prediction, I used Tracker to extract data from the video of the falling object. I obtained the initial position and the change in time as the object was falling, which will both be used for the computational models. Since the object was only being dropped and not thrown downward, we assume that its initial velocity is 0. As you can see in the graph obtained from Tracker, the slope of the position time graph is not constant, and therefore does not have constant velocity. I should note, however, that by 0.4 seconds, it does seem close, if not is, at constant velocity. The initial conditions from the tracker were used in the computational model as shown by the first few lines of code in Glowscript. As a reminder, Newton's second law states that the net force on the system is equal to the change in momentum over change in time. Net force can also be thought of as the sum of forces acting on the system. With this information, net force can be used to calculate the velocity and position of the object at a given time, as represented by the velocity and position update formulas shown on the slide. The while loop in the code demonstrates the iteration of Newton's second law to create a more accurate prediction of position and velocity over a long period of time. The object's velocity is used as average velocity, as we do not assume that the forces acting on the object are constant, which is why it is valid to use the object's velocity as average velocity in the position update formula. In the first computational model, we assumed that the only force acting on the system was gravitational force. Gravitational force on Earth can be calculated using mass times gravitational acceleration on Earth, which is approximately 9.8 meters per second squared, which is derived from this general formula for gravitational force. The force of gravity is acting downwards on the object, which is why gravitational force was negative. As you can see from the graph, there is a large variation between the computational model and observed model, which may signify that there are other forces acting on the object that were not accounted for in this prediction. Now, if we consider drag force in our net force calculation, we see that the second computational model aligns more closely with the observed predictions. The particles in the object's atmosphere interact with the object itself and is represented by the drag force, which explains why it shows a more accurate graph of the falling object. The crumpled piece of paper had a relatively large drag force because there were many places where air could affect the paper's motion. The larger the surface area is, the larger the drag force. The following position time graphs and velocity time graphs show the difference between the computational models before and after the drag force was included. In comparing the 3 different predictions, we can conclude that considering both gravitational force and drag force and applying Newton's second law on the system is important in creating more precise predictions for the motion of a falling object. However, it is also important to note that while the computational model that includes gravitational and drag force improved the deviation of the first computational model from the observed predictions, there is still a slight difference in the middle of the data between them. A number of conditions could explain this variation. There may be other forces in the object's surroundings that interacted with it but were not included in the model. The camera may not have been perfectly aligned with the ground during the recording of the falling object, so tracked positions could have been slightly off. The frame accuracy of the camera may have been off as well, so actual position of the object in between frames may not have been clearly shown. Regardless, the computational model with the drag and gravitational force is still very reliable in predicting the object's motion. In looking at the velocity time graphs of the computational models, we can conclude that the model that included both gravitational force and drag force predicted a terminal velocity. Terminal velocity is the specific speed that the object cannot exceed. As the object is falling, the drag force slowly increases to the point that its magnitude is equivalent of the gravitational force. However, since it acts opposite of the gravitational force and the object's motion, the drag force cancels out the downward force of gravity, resulting in a net force of 0, which means the object reaches constant velocity or 0 acceleration. The velocity time graph obtained from the second computational model shows the crumpled paper starting to reach terminal velocity at about 0.4 or 0.5 seconds. If the object was initially thrown downward at an initial non-zero velocity, it would still reach terminal velocity, but much quicker than when the initial velocity was zero. This was shown by plugging in a non-zero initial velocity in Glowscript and running a model which resulted in the velocity time graph shown in the slide. Thank you.